Saverio Bolognani is a senior researcher here at Zurich. Previously, he was a postdoc at MIT, at Leeds, and he got a PhD in Italy in Padua. Please, Saverio, now the stage is yours.
Thanks a lot, Andrea. So what I'm going to cover in this next couple of hours, actually, it's really the tutorial part of this tutorial in a way. It's an introduction, or it's a guided tour over like game theoretic models for dynamic interaction. So this is not really a crash course in game theory. It's a selection of topics that we have, that we consider particularly relevant for the topic of this tutorial. As Andrea was saying, this is going to be presented in a way that even without a background in game theory, one is able to follow. Actually, I think that by following these couple of hours in 2 parts, you're going to have all the notation and all the tools to enjoy the 3 following talks a little bit more. On the other hand, this is not self-contained. So there will be links and there will be pointers in during these slides to additional material, including the script or the documents that we're going to make available on the website, where some more references are going to be available and so on. But I hope that I can touch all the points they want to touch in terms of interesting topics and relevant topics that might be useful if you want to put together game theory and path planning, dynamic interaction, robotics, trajectory planning. There are 3 main sections of this tutorial part. The first one is really basic concept and definitions. This is as basic as it can be when it comes to game theory. Then there is a second part, which is special games and how to solve them, either computationally or what structure can you use to solve these kind of games. So here we are going to look at 3 possible, 3 classes of games which are particularly relevant according to us. And these 2 parts together are going to be covered more or less in the first hour. In the second hour, we're going to cover multi-stage games, which you will see it's extremely relevant for the topic at hand today. And it's going to be a number of things I would like to cover, which end basically with the tools and the notation that you need in order to start working and playing with this kind of results. Okay, so let's start with basic concepts and definitions. Very broad definition and very high level definition. Game theory is the study of mathematical models of conflict and cooperation between rational decision makers. So there's a lot to process in here, right? So first of all, it's mathematical models. So of course, the key point here is to take the process of decision processes by rational agents and to try to present a mathematical model for that allows us to either predict what these decision makers will choose as a decision, or to mandate some decision, or to instruct them on how to decide efficiently. We're going to see later what does it mean to solve a game in game theory. But at a very high level, you need several ingredients to characterize a game. So you need to define what are the players that make the decision. So actually, in the topics that we're covering today, this is the easiest part because, compared to other applications of game theory, here players are probably autonomous vehicles, robots, drivers, right? They're truly agents in the real world. Then you need to decide what actions are available to the players at each decision point. Okay. Again, application specific, but this would be like how to move or what kind of inputs, right, the system can receive. Then you need to define what is the information structure. The information structure specifies what the player knows before making each decision. So for example, but we'll see better later, for example, does a player know what's the decision of another player before making his own decision? Okay. And then when everybody has made their own decision, then you would have an outcome of this game, which of course depends on all players' decision in a joint way, otherwise the problem would be uninteresting. And the outcome is what players care about. Okay. So let's see an example, a very simple example about joint maneuvering. So here, what's the story behind this game? So we have 2 cars, the red car and the blue car. they are driving in the same directions over, two separate lanes. But the car on the left, at some point, detects an obstacle in the middle of the road. And now, so the two players has obviously the two cars. What are the two actions available to both of them? Well, one action is just to remain on their own lane, which means for player one to collide with the obstacle, for player two to just drive, stay on the same lane. The second action available to both players is to swerve to the right. Okay, so we're simplifying the game. Here there's only two actions, right? Swerving to the right means that, well, you invade either the other lane, or you go onto the grass at the side of the road, the shoulder of the road. And these, of course, have consequences. Now, the outcome or the consequences of this decision depend, of course, on the joint actions of the two players, right? And you could quantify them. So that's what we have done here, and quantify them in terms of, imagine like the economic damage to the vehicle or something like that. Okay. So what happens, these four cases are just the result of players picking one of the two actions. And because there's two players, we have four possible outcomes. So what happens if they both decide to swerve to the right? Well, in that case, player one, the red one, doesn't incur any cost. Player two incurs a small cost because he's driving on the shoulder. What happens if player one decides to stay on the lane and player two decides to swerve to the right? Well, then they both incur a cost, like the cost of hitting the obstacle and the cost of swerving into the grass. What happens if they both remain on their lane? Well, you can imagine, like, one of them hits the deer and the other one doesn't incur any cost. What happens if the first one swerves and the second one remains? Well, they incur the largest cost of all, both of them, right? That's, let's say, 100, right? Here we're just playing with numbers. Okay, so now we need to introduce some more formalism, after the cartoon. So the two players, we call them P1 and P2. We call capital gamma and capital sigma the two sets of actions available to the two players. So gamma 1, gamma n, in that case it was only two, and sigma 1, sigma m, in this case, again, only two actions. The outcomes are the cost function that they want both to minimize, and they're different for the two players. They depend on the joint decision. There's a compact representation every time you have finite actions and only two players, which is the matrix representation. And it's quite intuitive, right? It's basically the matrix that you've seen before with the plots, but in mathematical form. So in every block of the matrix, what you have is basically the pair of costs for the two, or outcomes for the two players. Of course, formally, this means that the element Aij for the outcome for player one is the result of player one playing strategy I, player two playing strategy J, and Aij describes the cost, capital J1 for player one, and similarly for B. I'll try to stick to the two colors, red and blue, for the rest of the slides until this is not too confusing. Okay, so what does it mean? Okay, now you have a game. What does it mean to solve this game, right? Well, it means different things, depends on what you have in mind. In general, I would say it means either to predict or compute or mandate a couple of strategies. So why is this difference? Well, because sometimes you have no control of the players. For example, you're observing human players, human drivers, but you want to predict because you assume they are rational players. In other cases, you can design, you think of autonomous vehicles, you can design what they should do, and you want them to be selfish but rational and to be able to decide on what's the best thing to do. In some other cases, you can even decide to mandate something. So you could have a centralized, benevolent dictator that decides what's the best behavior by both, but in a way that everybody's happy. These are just different flavors of what does it mean to solve a game. But the key idea behind the solution of a game is that you would like to find a pair of strategies so that no player can do better by unilaterally changing their decision. This doesn't say anything about other strategy pairs in which both of them change the decision, right? But unilaterally, they cannot, they're not better off by changing their decision. Similarly, or perfectly equivalent, players should show no regrets after they observe the outcome, right? They make the decision, they observe the outcome, they wouldn't go back in time and change their decision. There's a third interpretation, which is a little bit tricky, if you want. It's that if player repeats the game after playing these two strategies, then none of them is going to change the decision. This is not always true, right? A repetition of the game actually creates a different kind of game, right? But you could imagine that players are happy with their decision. They don't want to go back in time and change their decision. And for all this interpretation, the key idea is the concept of best response. So what's the best response? So best response for one of the two players is the set of actions that minimize their cost, their outcome, right? Given the other player action, sigma. So you see the best response is parameterized in the other player action, both for player 1 and for player 2. In general, this is a set of solutions, right? There might be multiple actions that lead to the same outcome. So it's a set of solutions, and this set of solutions guarantee the best possible outcome as a function of what the other is doing. That's really the key definition for game theory, right? You need to be able to tell what's the best response. The Nash equilibrium, it's simply the fixed point of best responses. What does it mean? It means that if you have a two-player game and they have their own two payoff functions for P1 and P2, then we call a Nash equilibrium a pair of action gamma star and sigma star, such that gamma star is the best response or is in the best response to sigma star, and sigma star is in the best response to gamma star. Okay. Of course, the complication of what a Nash equilibrium is comes from the coupling between these two conditions, right? I said it's a fixed point because it's naturally what it is, right? The two pairs together are best response to themselves, just of course in a symmetric or coupled way. And before I told you about the two the matrix representation for games, that's exactly the same thing. Like if your game is represented as a matrix, then a Nash equilibrium, it's literally an inequality condition over the same column of the A matrix and over the same row of the B matrix, which is interesting. Like for every element of the matrix, to tell if it's a Nash equilibrium, you need to only look at that row and that column, right? It's independent from what's happening in the rest of the matrix. Good. Okay, so what are the Nash equilibria here? Well, it's using the no-regret strategy is pretty clear to tell, right? So the one here on the bottom right, it's a Nash equilibrium because none of them regrets the decision. None of them would go back in time and hit the deer instead, or stay on the lane instead, because it would lead to higher cost. This is also a Nash equilibrium, right? Because none of them regrets the decision. Player 1 doesn't regret hitting the deer because swerving to the right would have caused a worse accident. And player 2 doesn't regret staying on the lane because swerving to the right would have caused some unnecessary cost. Of course, you can do the same. You can just do it in the matrix, or you can do it using this fixed point interpretation that I just provided you with. The best response of player 1 to remaining in the lane, so to player 2, blue, remaining on the lane, is to remain on the lane. And the best response for player 1 to the one swerving, to player 2 swerving, is to swerve as well. Okay. Similarly, for player 2, the best response to remaining is to remain. The best response to swerving is to swerve. And so if you look at what are the fixed points of these equations or of these sets, what you get is that the two Nash equilibria are to remain with outcome 30 and 0, and to swerve with outcome 0 and 10, okay, for the two players respectively. Now, a couple of simple observations in this apparently simple game. Nash equilibria are not interchangeable. What I mean is that you cannot define for player 1 the set of Nash equilibria and for player 2 the set of Nash equilibria and then mix and match. If you take remain and if you take swerve for player 1 and player 2, they both belong to a Nash equilibrium but to a different one. And in fact, the remain swerve is not a Nash equilibrium. And same for the others. Which poses an interesting problem, right? How do you what's your prediction if you have multiple Nash equilibria? And if you are instructing cars to behave in a certain way, what's your way to select one of these Nash equilibria? This problem is actually quite complicated, despite its, how early it appears in the slides. It's quite complicated to solve. I'll provide just one tool, and then we'll discuss some others, and some cases in which this problem actually becomes much easier. But one tool is to at least observe that Nash equilibria can be ordered, at least partially. What I mean is that if I take two Nash equilibria with the two outcomes for the two players, I can actually tell whether one is less or equal or precedes the other if both players are happier with the first one compared to the second one, right? So what's happening here is that in a fictitious here Nash equilibrium, player one is getting an outcome of -1, player two of 0. Both of them prefer, if you want, this Nash equilibrium to compare it to another Nash equilibrium which has outcome 1 and 2. Okay. Notice that this order here has nothing to do with the order that we used before when we were describing Nash equilibria. So here, in order to select one equilibrium instead of the other, both players need to change, right? So they are both actually perfectly valid Nash equilibria. They just prefer one compared to another one. Okay, you can actually draw them. So in complicated games, you have multiple Nash equilibria, and you can draw, typically what people use is a Hasse diagram that basically has a vertical line, an edge, every time one Nash equilibrium or one element of the poset is smaller or equal than the another one, and there's nothing in between. Of course, there's also Nash equilibria in a partial order set elements, which are not comparable. In this case, player one would prefer this one, player two would prefer the one to the right. Now, the minimal elements of this set, which is not a unique element in general, are what are called admissible Nash equilibria. So admissible Nash equilibria, or conversely, as a definition, a Nash equilibrium is admissible if there's no other Nash equilibrium that is better for or equal for both players with at least one of the two inequalities strict. Okay? If they are incomparable, like this one, or if they have the same outcome for both, then they're both admissible. And you can have more than two, right? You can have many admissible Nash equilibria. So this is a first or very simple but still practical way to select Nash equilibria. If you have multiple Nash equilibria, you might end up, or you might at least exclude the Nash equilibria which are not admissible, because both players, if you give them enough coordination capability, communication, computation, they will probably at least pick one of the admissible Nash equilibria. Think of this as a Pareto front of the set. Unfortunately, in the case I presented before, we have multiple admissible Nash equilibria which have different values, are not interchangeable, and in the case of the deer on the road, they were also not comparable. So they are both admissible by definition. As I said, this is a simple example, but this actually contains one of the key observations that in a way motivated also us to prepare this tutorial. If both players were to be very conservative, think of them deciding to do some sort of robust control, right? They want to consider the worst possible outcome, which is called security strategy in games, and apply that, then they do Nash equilibrium as an outcome which is worse than any Nash equilibria. So there's something to gain in at least playing the game, but then you need to decide which one you would like to agree on. One thing that we're not going to cover today is a mechanism design, which is the possibility of changing the game, for example, fine incentives, in order to make the game easier to predict, or the solution of the game easier to predict. It's not something we're going to cover today, but the idea is that you can make the desired Nash equilibrium admissible if you're allowed to change the cost for the players. For example, a fine, if you change the lane and you hit another car, would make the swerve Nash equilibrium more expensive for both, or at least for player two, which is what you care about. Okay. Having said that, let's consider another game. Again, a toy example from robotics. Imagine that there is a robot and needs to reach some safe zone at the end here. Now, the robot can take multiple paths, let's make it simple. You can go to the left, you can stay in the middle, or go to the right. And there is an adversary that is able to block one of these three paths, right? And by blocking, I mean to draw X. Okay. Again, it's the example where these two players need to make the decision at the same time. So at the same time, there is a synchronous moment where both of them decide what path to take and which path to block. Now, because here it's literally a game, player one wins if he reaches the finish line safely, and player two can block one of the three ways in order to win. You can just assign an outcome of +1 or -1, depending whether you lose +1 or you win -1. Okay, so if player one decides to go left and player two decides to block the left path, then player one gets a higher outcome and they are minimizer. Player two gets a -1. Okay, just in this game, at least not in the way that we defined before, right? Intuitively, because there's clearly no solution that presents no regret for the agents. If you look at the math, it's because the reaction set to going left, of course, is to block left for player two, but the reaction set to blocking left is to go on any other direction which is not blocked. And this is true for any of the three paths, right? So there is no fixed point in these best response maps. Again, not surprising, if you had to play this game yourself, what you would do is to introduce some randomization, right? And this is the natural and necessary extension of actions in games, which is the randomized play. What we do here is to define what is a mixed strategy, and the mixed strategy is simply a vector of probabilities associated to each action. So let's look at player one only first. If you have 1 to n, the actions for player one, gamma 1 to gamma n, then a mixed strategy is a vector y, which presents probabilities of player one playing strategy 1 to player 1 playing strategy n. And of course, these are probabilities, so they belong to the simplex, where the sum of all probabilities is 1 and they are all greater or equal than 0. Same for player 2. Now, with this in hand, what you can do is to define what's the expected outcome of a game, and the expected outcome is simply the weighted sum of the possible outcomes. Deterministic strategies are just a special case of this one, and we call them pure strategies if you want. And notice the definition: strategy is either pure or mixed. The actions are the n possible actions. Okay, why I said this is a necessary extension, because if you define mixed Nash equilibrium exactly as we defined the Nash equilibrium before, in terms of each element being the best response, so none of the players being able to improve their outcome by unilaterally changing their mixed strategy, which is exactly what you see encoded in here. That's a big enough search space for strategies that guarantees that a Nash equilibrium exists. In fact, Nash existence theorem is exactly saying that a mixed Nash equilibrium is always guaranteed to exist, not only for 2 players game, but for n player games. The proof is it's a fixed point proof. It's not here in these slides, but it's going to be, if you follow the link, if you go back to the web page of the tutorial, it's going to be in the little monographs we're going to post there in the next few days. Okay, and it's a relatively short proof, as long as you use a powerful theorem like Quaternius fixed point theorem, which is longer to prove than Nash theorem. Okay, now we've covered what I wanted to cover in terms of basic concepts. We're going to go and look into some special games, zero-sum, potential, and congestion games. So we already saw a zero-sum game, actually. The escape game, right, where this robot has to reach the safe space without being intercepted. If you can, you already noticed, of course, that all the outcome for every pair of actions sums to 0 for the 2 players, right? So if these conditions is satisfied, then we call the game a zero-sum game. and the Nash equilibrium condition in a zero-sum game becomes a saddle point condition. In fact, you see the optimal strategy is sandwiched in between what player 2 can do, which is always lower, and what player 1 can do, which is always higher, once we have defined that player 2 is now a maximizer and player 1 is a minimizer. Okay? It's simply a more compact way to represent the same game when this property here holds. Notice that we also dropped the subscript 1 or 2 to J because there's only one value of the game. And there's multiple interpretation of this one. The most obvious one is the one you see in the toy example here. It's adversarial agents. But very common cases of zero-sum games happen when you have a robot, a player, an agent against nature. Like you think I'm not sure if Alex is going to present this later, but he has a work when one of the two players is the road, is the curvature of the road. Like the road is playing against your car by presenting you with the worst possible turn in front of you, right? And there are also games like security games, for example, which is a very nice topic that we are going to slightly touch at the end of these slides, which are not zero-sum, but you can show that they are equivalent to zero-sum. So you can do enough transformation to make them zero-sum game. So for zero-sum games, because we're talking about robustness, we can talk about what are the security levels, or in particular, the mixed security levels. So high-level definition, these are the best things the agents can do, assuming that the other player is allowed to respond, right? So look at this one for player 1. This is the best minimum of the cost function, J of YZ, when player 2 is allowed to maximize after player 1 has made this decision. So this is the mean of the max. That's very conservative, right? It seems very conservative. So this is what player 1 can do if it can only announce its strategy and see to player 2 responds, and they get the outcome. So in general, player 1 should be able to do better than that. So this is an overbar. This is an upper limit. The underbar is the opposite, right? It's player 2 that can pick first, but needs to announce to the other player, and player 1 can respond. So this is an underbar, underline V, right? That's, at the end, you get something larger than that if you play, the game. And the mixed security policies are just mixed strategies that achieve these two. So the Y bar is exactly the argmin of this minimization, of this min max, and the Z bar is the argmax of this max min operation. These seem very conservative. This is like what you can do if you cannot play simultaneously. You need to announce your decision and then see how the other responds. Well, there's a theorem that says that these two levels actually coincide. So announcing your decision or not announcing your decision doesn't make a difference in zero-sum games. And if you take the two Nash equilibrium, these security policies, they're actually what you should play. They are the Nash equilibrium strategy. Okay? The proof is pretty simple. Actually, the proof in the monograph is much simpler than the original theorem. The original theorem, due to von Neumann, it's a long minimax theorem. The proof that we're going to include in the monograph is actually a shortcut using Nash theorem that does not require the complication of von Neumann results, which phenomenally, by the way, was an ETH alumnus. Why are these zero-sum games important? Well, the first one, we're going to see it in the next slides, is that zero-sum games are easy to solve. Nash equilibria can be solved by linear programming. The other thing is that if you notice here, the problem of multiple Nash equilibrium disappear. There is one value of the game. All Nash equilibria will have that value. This simplifies things a lot, especially once all Nash equilibria are also interchangeable, because here what I said is that you can take any security policy from the two players and you get a Nash equilibrium. So this means that once you solve the two security policy problem, you get all the Nash equilibria of the game, and you don't need to coordinate which one you're going to play. That's irrelevant. All of them are Nash equilibrium, and all combination of them are Nash equilibria, and they're easy to solve via linear programming. just one slide on how how would you solve this with linear programming. Well, you solve it with linear programming because you don't look for a saddle point, you look for a security strategy. You solve what happens to be also the value of the game, but it was not for non-zero sum games, but it is for zero sum games, which is the min max for player one, right? A min max over something which is bilinear in the min and max, it's an easy object to compute. Mostly because if you take the nested inner problem here, the maximization of a linear functional here, you know that the maximization happens at one of the basic feasible solutions. Like in linear programming, when you have a linear cost, there's always a solution which is at the intersection of n constraints, right? If these n constraints, if the dimension of the space is n. This means that the best response, so the max in the inner max here, it's a pure strategy. It's one of the pure strategies. This is something you probably observed already, right? If in the game here, player one decides how to randomize their trajectories and player two knows it, well, the best response is one. It's a singleton, right? You would just go and hit where the robot is going to go with the highest probability. Now, once you do this, then you realize that the entire thing is actually a linear program where all these basic feasible solutions can be used as constraints. So you're trying to push from above a V, a security level, such that no matter what player two does, you get an outcome which is better or equal to that. And this gives you security strategy, which is a Nash equilibrium. Notice that something that I found very interesting in zero-sum games and in games in general is that typically computing your best response gives you a pure strategy. The reason why you randomize is not to achieve a better outcome. You randomize to prevent the other from taking advantage of you. Okay, and that's exactly what you see in this linear program. Okay, we're going to see another class of games now, which is not a zero-sum game, and it's the class of potential games. It's the second class of games they wanted to present. So first of all, we need to generalize a little bit the notation that we've seen until now. Now games have n players, okay? So imagine that these n players, now we need to be a bit careful with the definition. The gamma little I is not the ith element to player one, it's the strategy for agent for player I, okay? We have I players. I mean, there's only so many subscript and superscript we can put. And a very common notation in game theory is that the gamma minus I is the vector of strategies of all the other players, okay? So the best response is defined exactly as it was defined before, is the argmin for player I, in this case, to what all the others are doing, gamma minus I. There is one generalization here that I'm not going to cover, but it's relevant. It's what are called generalized Nash equilibrium problems. So here you see the strategies or the actions available to player I are a set, capital gamma I, which it's given and fixed. You can actually extend a lot of these results to the case where this gamma, capital gamma, is a function of what the others are doing, which makes some sense, for example, in robotics application where you want to avoid collision. Like once you know the paths of the others, you're restricting your possible actions. This requires some care, and there's going to be a couple of pointers to papers on that you can use as a reference. Okay, so once we have defined this notation, what is the class of potential games? Well, a game is a potential game if there exists a potential function from the strategies to real numbers, such that for every player I, the gain for player I that player I can achieve in its outcome by switching from gamma I prime to gamma I second is equal to the change of the potential function where you replace gamma I prime with gamma I second, with all the other strategies by the other players remaining the same. And this needs to hold everywhere, right? For all possible gamma I and gamma I prime and gamma I second, and for all strategy of the other players, and for all players. Notice that what's complicated, why is this complicated to achieve, or is not in general true, is that the P here is the same function for everybody, right? It's the same potential function of the game. Okay. So in general, this is not true. In some classes of games, and we're going to see an example in a second, this is true. Why would you try to find games with such a property? Well, because if you move if you connect the outcome of all players to a common function, then for free what you get is that all pure Nash equilibria of the original game are the directional minima of this potential, right? I omit the proof, but the proof is by construction. Like if there's no gamma I second that allows me to increase the potential function once I am at an Nash equilibrium, this means that there is no gamma I prime that player I can use to improve or decrease their cost function. Okay, and there are two useful results here. The first one is that we know that we have to look for pure Nash equilibrium. I mean, there might be a mixed Nash equilibrium, but we know pure Nash equilibrium exists. And there are good reasons and good applications where pure Nash equilibrium are preferable. And the second important aspect of this result is that the directional minima are an optimization problem, not a fixed point problem, right? So if you know that your game is a potential game, then you can connect that your problem of finding Nash equilibria, which in general is a complicated problem, becomes a nonlinear optimization problem, for which I would say, a large toolbox of methods exists. And I'm not saying it's necessarily much simpler, but it's definitely a well understood problem. For example, one method that is allowed to converge, or that is guaranteed to converge to directional minima, is Gauss-Seidel, right? This is the method where you take an optimization problem in multiple variables and you minimize variable by variable. You start from the first one and you find the minimum, and then you start from the second one and you minimize over the second one by keeping the first one still at their new value, and then the third one, and so on. And you cycle through the coordinates until you converge. This is a method that you can just take from nonlinear optimization and use it to find the Nash equilibrium. And in fact, it's specifically very practical for the solution of a potential game. That's what is called, but it's just a matter of calling it with different names, iterated best response. So what you get for almost for free for potential games is that iterated best response is guaranteed to converge to pure Nash equilibria in a finite potential game. Now, in the case that I had before, first of all, you can check yourself. This is actually a potential game. So if there is a potential that satisfies the condition that I presented before here, right? And so this is a potential game. And so we are guaranteed that iterated best response in this case would converge to a Nash equilibrium. Now, in two players, iterated best response tends to be quite trivial. One of the two announces what he wants to do and the other one responds. So player one, I don't know, signals to the other one, I'm swerving to the right. And player two, well, does the best response to that, which is to swerve onto the shoulder. And this is a Nash equilibrium, we know it. The other case is that player two decides I'm going to stay on the lane, and player one then decides then I will hit the deer. Now, of course, whether this is a protocol or just a mathematical artifact, it depends a bit on the application. And here, the whole point is that the first player to decide needs to commit, right, to their decision, which in many cases might sound like an incredible threat, right? So, for example, the threat of saying I'm going to stay on the lane no matter what you do. Well, unless you throw your steering wheel out of the window, player one will probably not believe you so much. But this is beyond the toy example, right? It's an interesting problem. Non-credible threats are actually an interesting aspect per se of non-zero-sum games. Okay, so in computational terms, every time you have a yellow box in these slides, it's a new computational method. So at the end, you're going to have 6 or 7 of them. An iterated best response starts from an initial strategy for all players, a counter at 0. And then if this is a pure Nash equilibrium, you stop. That's an easy test. If it's not a Nash equilibrium, there must be a player that can improve. So for which their current strategy is not the best response to the others. And then let this player improve and pick a new strategy which isn't the best response, while the others maintain the same strategy. And you rinse and repeat. Okay. So it's not only a computational method, like as you can see, could also be a distributed negotiation protocol if you want, because what we are doing here is that each player, they need to know only their own cost function to compute their best response. So it's really distributed and private in a way, right? Different players can update their decision without sharing their own preferences to others. The main complexity of this game, of this solution, sorry, this method to solve this game, is that it converges to an Nash equilibrium that depends on the initial conditions. Depending on where you start, you converge to a different Nash equilibrium. And not only to admissible Nash equilibrium, you could converge to any Nash equilibrium. This is the simplest version. If you have games with continuous action spaces and not only a finite action spaces, you can also apply iterated the best response. And if you have generalized Nash equilibrium problem as before, you can apply iterated best response. But you need to do something, either regularize it or to be happy with some epsilon value of it. There's going to be a couple of pointers in the monograph about that. But the core idea is more or less the same. Okay, third class of games that I wanted to present is congestion games. So congestion games are a game. So potential games were a bit tricky, right? So they had a very peculiar mathematical property. And then it told, this gives a lot of nice results. So you might actually want to check if it has this strange property. Congestion games is a little bit the opposite. In congestion games, the setup is very reasonable. And it's the following. You need to have a set of resources, calligraphic M, right? These are possible resources that you need to share across the different users. And the strategy for a player is to use a subset of the resources. So for example, a player could use resource number 4, right? Or he could use resources number 2, 4, and 6. Okay. Of course, once players make their decision, each resource will have some load. The load is just the number of players that are going to use that resource. Now, if a resource is used by many players, then it actually comes at a cost for the players that are using it. And so the cost for player I is the sum over all the resources that player I is using of a function fj, which is the same for every player using the resource j, of the load of players using j. Okay. So this is a specific structure, but it's actually quite common to observe. So one example is this one, right? So here, the resources, maybe I can do something better than that. The resources are, for example, parts of the intersection. Players need to decide, the yellow player is going to use these 4 portions of the road. And the blue player is going to be this one and the one turning to the left. And player 1 would also use to use this one, okay? So that's a congestion game. A very common example, which is also in the monograph with all the details, is routing problems. Routing problems, agents, like 100 cars, need to decide what path to use, like the road, the ferry, the bridge, or what. And of course, the time they spend driving or the time the delay of the ferry might actually depend on how many people are using it at the same time. That's a perfect example of congestion game. Okay. And it's actually, where the name congestion comes from. So if your game has this structure, then you can use the fact that congestion games are potential games. In fact, you can prove that the potential function is known and is known in closed form, is the one that you see listed here. And the proof requires a slide and a half to prove that this is actually a potential function. And congestion games happens everywhere. Historically in data networks, communication, like how many users are using the same communication channel, traffic, manufacturing, power grids, but I argue also robotics and dynamic games. Notice one thing, if you look at this cost, even if you don't need to parse exactly what's in this potential function, one thing that is important that is different from the social cost. The social cost would be the sum of how much time people are spending on a path like fj of lj times all the people on that path. That's different from this potential. I mean, there's no rearranging of the indices here that takes you from P to W. In fact, a common observation in many congestion games is that the solution, the Nash equilibrium of a congestion game, are typically not the best from the societal point of view, which is called Bryce paradox, and which is can be quantified through the concept of price of anarchy. Both these things are in the monograph, specifically presented for these results. So you can see here the emergence of this kind of behavior. And in fact, that's not a mathematical artifact or a mathematical curiosity. If you allow people to be selfish in the use of shared resources, people or robots, then what you get is that the shared resource is used usually in a non-efficient way. Okay, there's going to be an extra price for the anarchy that you have allowed of people being selfish without following your directions. Okay? And even if this was known from well before map apps and Waze and Google Maps were a thing, this has been observed now. The routing and the traffic, when there is a heavy use of apps like Waze, Google Maps, Apple Maps, leads to traffic condition which is actually worse than the one when nobody's optimizing strictly for their path, and in particular when people were not aware of the decision of the other players. Okay, so this has covered the first two sections, and so from my side, that's what I wanted to cover in the first 45 minutes. We have a break before we start with the third part, where I can, of course, address questions, and we can discuss, and we can look at some of the things I presented together.
Saverio, I think most of the questions were already answered in the document, but there's one that came up at the end, which I think would be interesting. So the person is asking, what are common mathematical tools used in most of these proofs? What is in general a structure or approach of this proof? I think it was for the, yes, related.
Yeah, that's a very good point. So in general, unless you notice some structure like the potential function, a common potential function for the players, or a zero-sum structure, then game theory is mostly a matter of computing fixed points. And that has been like that historically, from the very, very beginning of game theory. The problem is that it's easy, or it's relatively, let me see if I can go back to this one. It's relatively easy to understand and to decide what's the best response. Of course, there's some optimization going on here, but you could also assume people can do the best response. That's the core of being rational. The complication comes when you want your decision to be the best response to the other decision, and the other decision to be the best response to your decision. And this is reflected definitely in the proof. Like most of the proofs here in the multi-stage part in the next hour and so on are variations where you have to prove that you are at a fixed point where one is the best response of the other. Now, depending on what is this best response, if it's a convex game, then you might end up using some results from convex optimization for both of these. In some cases, you have variational inequalities. In some cases, you have KKT conditions. We're going to see a couple next hour. But at the end, you're solving coupled optimization problem in a fixed point manner. The exception to that, it's zero-sum games where there's linear programming to solve things, or when you have some very special structure like potential functions, where you can actually you're actually solving minimization problems.